won the lottery. The prize is a rope of length 10 meters. The host tells you that you can have any piece of land which you can enclose with this rope. So the natural question arises, what is the maximum amount of area you can enclose with a rope of 10 meters? Or in general, for a fixed parameter, which shape gives the maximum area? Our strategy here will be to start with a random closed shape and keep making modifications to it that strictly increases the area while keeping the parameter constant and see what we're heading towards. First of all, let me argue that any concave shape cannot give the best area to perimeter ratio. Concave shapes curve inwards. More formally, if there exists 2 points in the shape such that the line segment is not entirely within the shape, then the shape is concave. For example, this yellow line segment here. Given this, if I reflect the portion that is concave about this line, the new shape formed still has the same parameter. However, if you look at the new shape, the area increases as the blue area is now part of the area while the orange area remains as is. For any concave shape, such 2 points will always exist by definition and therefore cannot give the maximum area to perimeter ratio. So we know the ideal shape will be some convex figure. Let's start with a random convex figure. Starting from any arbitrary point on this figure, let me walk around the figure and split it into half so that they have equal perimeter. Actually, I only need to focus on maximizing one of these halves because notice here if the blue figure has greater area than the orange figure, I can simply reflect the blue figure. This new figure, that is blue plus blue, will give me, for the same perimeter, a greater area than the blue plus yellow. So let us focus on maximizing the blue area and then we can reflect it to get the desired result. Taking any arbitrary C on our figure, we can form the triangle ABC. You can pause here if you want to try maximizing this by yourself. But the key observation here is that I have the freedom to vary the angle ACB without changing the perimeter. Notice here that the blue region along with the blue outline remains unchanged as I vary the angle C. We can also see that lengths AC and BC are unchanged. So now our question becomes, for fixed lengths XY and XZ, which angle X between them will give the maximum area? Let me reflect and shift this area to form a quadrilateral. The area of any quadrilateral is base into height. It took us 2 triangles to get here, so twice of area is base into height. Now let me drop from X a perpendicular line to YZ, also known as the altitude. This is our required height. So the base is B and height is A sine alpha. So we get half AB sine alpha. This only depends on alpha, the angle between them. Sine alpha is maximum when alpha is 90. Therefore, a right angle triangle gives the maximum area for fixed A and B. We're all adults here, I won't bore you with any more elementary geometry. Back to our figure. So we set this angle to 90 degrees, thereby maximizing the red area while keeping the blue area and the outline, which is the perimeter, the same. Essentially, we do this transformation with every point on the outline C where ACB is not 90 degrees. Eventually, we end up with a figure where angle ACB is 90 degrees everywhere on the outline. The only figure that has this property, as you would recognize, is the semicircle. There are hundreds of ways of proving this identity, I won't show it here. So we reflect this to get a circle and that is our desired result. The circle is the shape which gives the maximum area for a fixed perimeter. In particular, the area to perimeter ratio is pi r squared divided by 2 pi r, which is r divided by 2. And you cannot do better than this. Engineers might tell you that a circle is a bad design because you can't fit circles together that efficiently. But since when have engineers said anything smart?